Let us switch to solid rocket engine. Some of our friends may be unhappy that we did not discuss solid rocket engine till now. Let us do that. There are two kinds of propellants used in the actual systems. We have double base propellants and composite propellants, but most high energy systems now use composite propellants for their operations. Typically a rocket engine, for those who are not familiar with it, will be like this. You have an outer metal casing, is an inhibition system, a insulator, plastic insulator, then the propellant. You see the propellant here, as you see, cast into the outer casing, and it's got various geometries. Reason will be simple. You have to give the definite amount of burning area to produce the given thrust. The hot gas is going through the nozzle will need that amount of mass flow. That is why you have various geometries. You have ignition system here. The propellant, there is a very important fundamental principle. Every propellant burns along the local normal. So, you will discover that if it is in this format, you will find the propellant goes radially outwards. If it is at an angle, it is normal to that. In fact, you see all the arrows that I have shown here, this burns along this burns along this direction. So, the geometry will expand in its own way and the entire propellant will get burnt up after a while. Okay. This propellant, which has both oxidizer and fuel elements in it, once you ignite, you cannot do too much more. There are ways of extinguishing, but that is a more complex process, and you have to depressurize, you have to do many other things. So, once you ignite, you have to accept the fact that it will completely burn up. Typically, it burns at millimeter per second, which is very small at low pressures, around 10 to 11 millimeter per second, normal operating pressures of 40 to 60 atmospheres. Some propellants are designed to burn even faster, 30 to 40 millimeter per second. The operation, the burn rate depends on the composition, pressure and initial temperature. And this one key aspect which Dr. Varun will present in terms of modeling it, how to predict this burn rate given the composition and the conditions of initial temperature and pressure. Just look at qualitatively burn behavior. I think everybody should just know that much. You see some three pictures here. This is the burning of a propellant of a double base propellant, nitrocellulose, nitroglycerin double base propellant. You see that the flame is far off. This is burning at 10 atmospheres, this is burning at 20 atmospheres, this burns at 30 atmospheres. You see the flame is coming closer, the flame thickness is smaller. As pressure increases, the flame comes closer, flame thickness is smaller. That is the key point to observe here. And nitrocellulose nitroglycerin propellant is essentially homogeneous. That means the oxidizer and fuel elements are together. So, there is no other process than combustion reactive process which controls the behavior. It is a premixed combustion process. So, what we described as premixed combustion in gases applies here to solid propellants. Then we look at ammonium perchlorate, HTPB is hydroxy terminated polybutadiene composite propellant, typically used in all ISRO applications. If you look at pressures here, very small pressures, 1 atmosphere and something like that, this is shown here for expressing the following behavior. This is at 86% solid loading, these two are 86%, this is at 80% solid loading. You see the brighter flame, slightly more fuel rich compared to these two cases. Burn rate is also low at ambient pressure, is about 1.2 to 1.5 millimeter per second, the point which I mentioned a little earlier. But only if you go to higher pressures, say 650, 60 atmospheres, you will get burn rates of the order of 8 to 10 millimeter per second. You see the burn rate as a function of pressure is increasing like this, and typically expressed in a format like R dot is equal to APN. P is pressure, A is the coefficient, N is the pressure index, and this is called Wheel's law, the standard way in which the propellants are processed and analyzed. The only point to note is that A and N will depend on the composition and initial conditions. So, the burning behavior of homogeneous and heterogeneous propellants as a function of pressure and temperature and ingredients are shown here. And you will see that in this case, in the case of NCNG, it is premixed combustion, homogeneous propellant, it is premixed here, and if you have a larger particle size, then the oxidizer gases have to mix with fuel rich vaporized fuel fragments from H2PB and burn together. That is a diffusion process. So, you have both premixed and diffusion are taking place in a heterogeneous propellant, only premixed process in the case of homogeneous propellant. Just remember, the rate of temperature rise is extremely large, goes up to 10 power 5 K per second. If you see, it is 300 K at the surface, around 1000 K, and flame temperature is 3000 K, and you see the time it takes for it to burn is 10 millimeter per second, and the zone over which this occurs is about quarter of a millimeter or so, even less than that. Inside, the actual peak temperature occurs at maybe 50 microns from the surface, and therefore temperature rise rates are very, very large. Just keep this in mind, because many times tools which are used to analyze it are not necessarily compatible, and this is the point which will be brought out by Dr. Varun later. So, I am asking a question, can we predict the burn rate using a combustion principle? Clearly yes, and you can actually do an exercise given a composition what the burn rate will be, and this has been done for at least 100 compositions by them, including a team from VSSC quite successfully, and you will see the results. Stable and unstable combustion. I am showing here a motor with 2 meter long, 68 mm ID, about 200 mm OD. During the development of this system, and I will not say what it is here, it worked well with the pressure time curve, which is nearly same as what was predicted using normal principles. You will see achieved and predicted. In half of them roughly, during the development phase, you found pressure time traces like this, and this we can infer later to be a longitudinal instability with the pressure going up along the predicted line until some point and shooting up substantially, and there are two features here. The pressure is fluctuating, and there was change of the mean pressure, and this is called the DC shift, that the shift of the pressure from here to some other value around which it fluctuates. These are the features which occur. So, we should ask ourselves this question, why does this instability occur at all? What are the mechanisms and how do you overcome them? Now, there are important points for you to note. There is existing literature on the subject, which is I must honestly tell you is not correct. There have been analysis of this phenomenon which is directed to some nonlinear wave propagation techniques, which is really not right. It is related to combustion, energy that is coming from unstable processes to do conduction from the surface below the surface and interacting with gas phase. Matter again will be looked at later. Let us switch to liquid propellant rockets. It is a large subject, so let me take a quick overview. Liquid propellant rockets come in a variety of sizes and for variety of applications. Monopropellants like catalytically decomposed hydrazine, they are used to provide thrust for satellite control. Catalyst typically is called iridium coated porous alumina particle bed into which you spray the monopropellant. Because the spray hits it and the surface decomposition occurs of the decomposition of the propellant, in this case monopropellant hydrazine, occurs because of the catalytic activities at the surface, and you get gases generated. Temperature exothermically temperature build up to reasonable levels around 1000 to 1200 K, and then the gases go to the nozzle. Relatively small rockets using storable hypergolic propellants like monomethyl hydrazine and the nitrogen tetroxide combination These are used for delivering satellites into the orbit or orbit transfer maneuvers, including inert gas and helium nitrogen pressure fed arrangements for the liquid feed system. So, this combination is the hypergolic, which means it is self igniting. It means no need for separate ignition system. Larger rockets use storable hypergolic bipropellants as second or third stage propulsion systems, but with turbopump fed arrangements. You please see here it is pressure fed because sizes are small, these sizes are large. Sizes means in terms of both in terms of flow rate and the burn time they are large. That means the total impulse delivered by these engines is much larger than these, and in these cases you need turbopump fed systems to reduce the weight of the system and the size of the system. And then they also use a gas generator turbine essentially to pump the fluids to higher pressures, and the hot turbine exhaust goes through separate nozzles. This is one form in which the engines are constructed. Chamber pressure is typically 50 to 60 atmospheres typically. The upper stage larger rockets which use liquid oxygen and liquid hydrogen, these are usually more complex, but there is a more efficient staged combustion cycle. The products of combustion of the turbopumps will also go into the main combustion chamber, taking the chamber pressures to as high as 300 atmospheres. Now, I say 300 atmospheres in one engine under development at LPSC, it is around 170 atmospheres or so, but there are Elon Musk has developed used an engine from Russia, and that the chamber pressure goes up to 300 atmospheres. Larger lower stages use liquid oxygen and kerosene, again in a stage combustion cycle. In LOX kerosene and LOX hydrogen systems, the ignition system has to be separately included because the fuel and oxygen combination is not hypergolic. The engines become very compact with increased choice of pressure, chamber pressure, making the design difficult. In fact, in stage combustion cycle, the peak pressures go right up to 700 atmospheres, and you have to be very concerned about the pumps, seals to make sure no leakages occur. It is a very tough engineering call on the design of these systems. One of the features in terms of combustion is that there is a supercritical operating condition, and in fact, it needs a different equation of state. Equation of state is good at conditions where temperatures are high, pressures not too high, and pressures become higher, including supercritical conditions. The equation of state and the vapor will become very different, and the gas will be different, and this has to be treated in the design process or the analysis process. Look at, I am just showing the 3 engines. F1 engine is too well known in the literature. It was Saturn V. It took the mission to the moon. It happened several decades ago. This was the engine used. And the space shuttle main engine, which is the workhorse for the space, which was the workhorse for the space shuttle, and the RD-170 engine developed in Russia, which was the workhorse for them. All of them have various thrust levels shown here: LOX kerosene, LOX hydrogen, and LOX kerosene are the fuel oxygen combinations used in them. Okay, I am just showing you in terms of development, variety of things have been done in terms of small scale engine experiments, and there is a particular reason why I want to show you this diagram drawn from one of the research efforts. You will discover that the process of combustion, you will find fragments, portions where there is no flame and then there is a flame, and you will see that you may not see it right here. You will see some mixing zones shown here. Let us see something more. So, what are the processes which occur in the combustion chamber of liquid rocket engine? Injectors could be coaxial or impinging variety which generate liquid droplets. In coaxial systems, usually It is the gaseous oxygen and liquid kerosene interact to generate the kerosene droplets. So, you have oxygen coming at the center, your liquid droplets coming, your kerosene injected in the periphery, and then you create droplets along the way. In the case of impinging jets, which is what F1 engine was about, the impingement process generates liquid droplets. Larger injector hole diameter creates larger drops. Okay. This is shorter mean diameter, this is a volume to surface ratio based diameter. It's dependent on the injector hole diameter. This is a more accessible feature used to get better atomization. Injector pressure drops are typically 10 to 15 atmospheres across the injector and cannot be varied at will since the pressure but get fixed by the pumps. What I mean by that is you can't arbitrarily demand, like in diesel engine you remember several thousand bars, but here you can't do it because it means that the pumps have to build up their pressure. So, the injector pressure drops are limited because of that. You will see something interesting in this diagram. You will see the chemiluminescence picture of the combustion process here. You see OH star being tracked. There are portions where there is combustion, where there is no combustion. Let us keep this in mind. Very different environment. You are looking at fire, which is essentially uncontrolled combustion, something which we do it at Jain University. What you see here is this 70 millimeter diameter pool fire, and also you can also do the same thing at 2 meter pool fire as well. You will find the same behavior. You will find here a flame extinguished and another flame here. Okay. There is flame, therefore, the flame extinction at some points and ignition at others. This more easily noticed since the frequency is only 5 hertz or lower in these cases. But forced convection, which I showed you a little earlier, this will be at much higher frequency. You will find patches where there is extinction, there are patches where there is combustion. The key question is to determine the burn rate of the, in this case, you have to determine the burn rate of the fuel given the geometric parameters of the pan and why the flame becomes extinguished or not extinguished in the gas phase, and what controls the flame extinguishment process when of course foam is applied and in the gas phase as well. See, these processes have commonalities, something which we will address later. That is, why does the flame get extinguished when the flow is taking place? Why does it reignite later? These are important questions. And in a turbulent flow, it may mean simply an averaging process, but if it is not exactly so, you may find it as an expression of an unstable combustion as well. Okay, I want to summarize now. There is a variety of combustion processes following fundamental aspects at the least. Flames are either premixed, I did not mention partially premixed, they could be partially premixed, or diffusion. They have different fundamental behavior in terms of ignition, steady combustion and extinction. All these processes are influenced by whether something is premixed or diffusion. They will influence both efficiency, emissions and stability in most practical systems. It is therefore important to understand them. Premixed systems at stoichiometry have high heat release, but larger emissions. Premixed systems near limits are also unstable. Diffusion flames are more stable, but not as clean burning as premixed types. Practical combustion systems can be beset with local ignition and extinction phenomena, as I showed you, including in fires, high speed combustion system, composite solid propellants or liquid rocket engines. These need to be understood as well. So, I just have told you what are the aspects which occur in actual practical systems that we, by understanding the fundamentals, we will be able to derive the benefit of resolving issues which if they arise. I think that is all I need to say on this subject at this point of time.